What is the difference between a master and a slave? A master chooses, a slave obeys. Thankfully, slavery's been largely abolished in the civilized world, but there's one area where it's still at large: embedded programming. When we connect a microcontroller device to an I2C based device, we use the term master to refer to the microcontroller, while the I2C based device is referred to as a slave. In a master-slave relationship, the master decides when to start talking to a slave and when to stop. A slave can only talk if their master asks them a question. They are incapable of free speech, so they cannot initiate a conversation with their master. When we connect a microcontroller to a slave device, we connect two pins. One is the serial clock pin, and the other is the serial data pin. Every time a transmission is started, the master will generate a clock signal via the serial clock pin. You can think of it like a blinking light that's shining on the serial data pin. Both master and slave devices will only read the data that's on the serial data pin when the light is turned on. That is, when the serial clock pin is pulled high. The line of communication connecting the master and slave's serial data pins is bidirectional, meaning that this single line can transmit data from master to slave and from slave to master. Obviously, only one party can transmit to the other at one time. Once either the master or a slave takes control of the data line, the other can't use it until it's been released by the current owner. So what can a master demand of their slave? Well, it's just like any other external connection. They can either write data to or read data from their slave. Let's start with writing a single byte of data. Now, at the beginning, both the serial clock and the serial data lines are at an idle state, during which they are both pulled high. If the master wants to write some data to their slave, they need to tell their slave, "Hey, wake up, I'm about to say something." In other words, they have to send a start signal. This is accomplished by pulling the serial data pin low while the serial clock pin is high. After sending out the start signal, the master will start generating the clock signal via the serial clock pin so that master and slave can start interpreting the signals on the serial data line. Now, a master can have multiple slaves, so each slave has a unique identifier known as a slave address, which you can usually find in the datasheet of the slave device. So after the start signal, the master sends a 7-bit slave address through the serial data line to indicate which slave it wants to talk to, followed by a read-write bit. If the bit is 0, that means the master wants to write data to the slave. If it's 1, that means the master wants to read data from the slave. Since we're writing data, we set this bit to 0. Now the master needs to make sure that the slave heard them, so they'll release the serial data line to the slave, who will send back an acknowledgement signal by pulling the serial data line low. This acknowledgement has to happen every time the master sends a byte of data to the slave. You see, the master is very insecure and needs to make sure that the slave has heard every single byte they're saying. Once the slave has sent the acknowledgement, the master will take back control of the serial data line. Now, a slave device can contain multiple data registers with their own local addresses, so the master needs to specify which register it wants to write to. For example, free, which is followed by an acknowledgement from the slave. Finally, the master can send the byte of data that it wants to write. Once the slave sends an acknowledgement, the master is satisfied and can dismiss their slave for the time being. They send a stop signal by letting the serial data line go high, while the serial clock is also high. Immediately afterwards, the master will stop generating the clock pulse. So to summarize, the master first sends a start signal, then it sends the address of the slave it wants to write to, then which register of the slave it wants to write to. Finally, the data it wants to write, followed by a stop signal, And every time the master sends a byte of data to the slave needs to send back an acknowledgement. Writing multiple bytes of data is largely the same. The difference is what the master does after the slave sends an acknowledgement to the first byte of data. Instead of sending a stop signal, the master sends another byte of data, which the slave acknowledges. Then the master sends another byte, and so on and so forth until the master finally sends a stop signal, indicating that it has written all the data that it wants to. Now let's see how the master reads from the slave. Once again, the master starts off by sending a start signal by pulling the serial data line low while the serial clock line is high. Then it sends the slave device address followed by the read-write bit. Now, you might think that since this is a read, we'll send the read bit, 1. But we're actually going to send a 0, the write bit. You see, the master needs to tell the slave device which register it wants to read from, and so it has to write the register address to the slave device, which will store it in a temporary pointer. The slave will remember this register address when the master starts the read operation next. The fact that our read operation begins with, well, a write operation might seem counterintuitive, but let's think about it. If we were to, say, include the register address as a required input parameter to our read operation, it would make the I2C read operations more inflexible, since not all I2C devices have multiple registers, and even if they did, different devices might have different register address lengths. So it's simpler to send over the register address as a generic piece of data in a write operation rather than as an input parameter in a read operation, even if it means that an I2C read now requires 2 operations instead of 1. Anyway, after the slave acknowledges receiving the target register address, the master can start the actual read operation. In order to start a new operation, the master needs to send another start signal. Note that we don't need to send a stop signal first, because the master only has to send a stop signal if it has no more commands to send for the time being. But if the master wants to start another operation right away, then it should send another start signal right after the previous operation finishes. Now, the master sends the slave's device address again, followed by, this time, a read bit, 1, telling the slave it's going to read something from it. And remember, the slave already knows which register the master wants to read from, since the master wrote the target register address in the previous write operation. So once the slave acknowledges the master's call, it will send a byte of data from the target register to the master. This time, the master is the one who has to send an acknowledgement every time it receives a data byte. Now, if the master is only reading 1 byte of data, then it follows this up by sending a stop signal. But if the master wants to read multiple bytes, then it won't send a stop signal, and the slave will automatically send the next byte of data, and the next until the master finally sends the stop signal. And that's the I2C communication protocol. Thanks for watching.